Okay, so I want to welcome us to multidimensional scaling. Okay, so what do I actually mean by multidimensional scaling? Of course, this is very similar to principal component analysis. The only difference, let me just say in principal component analysis, we got a lot of features, okay, a lot of independent variables. And those variables are not truly independent. Some of them are highly correlated. And of course, the dimensionality is actually high. We apply principal component analysis to reduce the dimensionality. And of course, don't forget, at the end of the day, we still have the principal component extracted based on what I'm actually going to call the maximum variance C retail, or it's a linear combination of the old features. Okay, you know, but if you take a look at the multidimensional, scaling, I'm also going to say it's a statistical technique or a machine learning algorithm that we use in visualizing the similarity or dissimilarity of data in a geometric space. Now, if I have a dimensional data set, okay, or and now and I want to represent that visually, okay. So because it's a dimensional, it's not going to be easy at all. And of course, the traditional approach used here is when you actually go by heat map. And heat map, you generate pairwise scatter correlation matrix, and at the end of the day, the heat map comes with with an issue in the sense that because it uses color intensity. Of course, it will be difficult for you to be able to make a sense of what is unfolding. Okay, so this very approach will enable us to identify pattern in high dimensional data by representing it in a lower dimensional space. What do I mean? If I actually consider, let's say, in the high dimensional space, okay, if the distance between data point, okay, we also want to maintain that very distance between data point when it is projected into lower dimensional space. So I'm actually going to say this has a lot of application if you want to talk about in psychology and marketing, or you want to talk about in genomics and bioinformatics. We want to talk about sociology and anthropology. Of course, multidimensional scaling is actually very, very crucial because it's actually going to make a sense if I can project high dimensional data into 2D or 3D. That will be easy for accessibility. Not only that, that will convey, we can convey it, or we can read it easily. Okay, like I said, with the conventional heat map, the viewers are likely going to be overwhelmed. Okay, so because there's a kind of connection between the PCA, the principal component analysis, and multi-dimensional scaling. Okay, that's why we're going to have a recap right now. Of course, a PCA is also a dimension reduction, dimensionality reduction technique. Okay, and of course, the direction in the data, according to the PCA, is actually the one that will capture the largest variance in the data. Of course, you know that, and of course, what we normally want to maximize is actually the variance. Okay, so that's all we want to maximize, and PCA is a linear reduction method, and of course, we can also use a linear operator to create a low dimensional representation. Okay, so this is also similar, to CA or multidimensional scaling is similar to PCA. Okay, so what is the goal okay, of the multidimensional scaling. Okay, so the goal is actually, we're trying to map each item as a point in a low dimensional space. I mentioned the other time in a 2D or 3D scatter plots, instead of us to use its map that's could overwhelm the viewers. Okay, and you know what? When we actually trying to project data set in the high dimensional to low dimensional space. Okay, we want to do that in such a way that the distance between points in the low dimensional space reflect the original dissimilarity as accurately as possible. Even though I know there's going to be a distance, we don't expect the distance between data point in the low dimensional space to be exactly as the distance in the high dimensional space. Of course, there's always going to be a gap. Of course, what we're trying to do is we actually going to use a method that minimizes the gap. Okay, so if you're with the inputs here, we need a matrix of dissimilarity. Okay, so we know, the data themselves are not needed. I mean, the original data you collected are not needed because the original data is going to be, you have observation, against features, but what you need to do, you need a dissimilarity matrix, okay, from there. And of course, we believe or give it the similarity of between the features x1, the object x1 up to xn. Can we actually find a coordinate z1 or up to zn? Okay, such that the Euclidean distance between z's are as close to the dissimilarity between x's as possible. So what I'm trying to say here is if I have x1 up to xn, if they are the element in the high dimensional space. And of course, we observe their dissimilarity. By the time we find a coordinate or point that we call Z1 and Zn, which are actually the coordinate in the lower dimensional space, we actually want to see whether the dissimilarity in the original high dimensional space can actually also be captured in the low dimensional space. And of course, I told you about the application of MDS, this is dimensionality reduction technique. And of course, the dimension we're looking for is 2 or 3. And also I call 2D and 3D. And of course, this is very popular in psychometric, in psychology, in general. And also in marketing, where we want to visualize perceptions or preferences, okay, like plotting our consumer view or different brands. And also mention, this also used in genome-wise association study about informatics in general, where we actually are trying to map relationship between genes based on their expression or profiles. Okay, so because the inputs in MDS, involve computing dissimilarity that actually call distance. Of course, I want us to know we got different kind of the similarity measure. Okay, the generalized one is the Minkowski. Okay, you can see Minkowski here. So when Q equal to 2, you have Euclidean. If Q equal to 1, you have Manhattan, and if Q is sufficiently large, you're actually going to have that. And we also have Mayer-Lanobi distance that we use in classification. But you know what? The similarity, that we normally measure that we use is Euclidean distance. Okay, so we also got some measures of similarity measures, okay, like a cosine measure, the correlation coefficient, the Jaccard Tanimoto coefficient, because at times if you compute the similarity measure, we can actually from similarity measure to or can compute the similarity. Okay, so more on the similarity measure, correlation is one of them. Don't forget, in the heat map. Okay, so correlation it's actually what is projected on its map that I said the other time, that will overwhelm the viewers. Okay, so I said no, the similarity measures are not always positive. So if you are working with correlation and if the sign of the correlation is of no relevance, you can actually take the absolute value. Okay, and if the data are not centered, the cosine and the correlation coefficient will be the same. And of course, if the data are standardized, then the Jaccard Tanimoto coefficient is going to be that. Okay, so what if in a situation where you got similarity measure and you want to convert that into the similarity? Okay, these are the way you can handle that. So if Sij is this similarity, and of course, sorry, if the Sij is similarity, and I want to, determine the dissimilarity, this is what I'm actually going to do. Okay, and that would make sense for boundary dissimilarity. As you can see here, if Sij is a correlation, of course, if the correlation is similarity, so if I want to get the dissimilarity, it's just going to be 1 minus that. Okay, then I also have this guy, another way to determine the similarity. Okay, here we got parameter alpha and sigma, and those parameter actually are turning parameter, okay, in such a way that when you have a larger alpha or smaller or gamma, the faster the similarity approaches zero or as similarity increases. And of course, you would also have another form of similarity that actually going to be in our product. You can see a square here, right? Okay, so which is going to be that. Okay, so when you talk about the similarity, of course, we could have, when you have features, the features could be, if you want to put into consideration the scale of measurement, it could be ordinal or it could be categorical variables. So, if I have ordinal variable, we can actually code that from 1 to n, and we can apply continuous measure. And of course, if you have a categorical variable, of course, we all know the simpler the similarity measure is actually going to be 0. And of course, that is where S equal to Y. So which means it's just like I'm talking about city of Chicago and city of Chicago. So if Chicago city equal to Chicago city, S equal to Y. And of course, if I have two different city, maybe I'm talking about the New York City or I'm talking about Chicago City. Of course, I'm actually going to have a label of 1, where that means S is not equal to Y. And of course, we can have a kind of refinement based on the subject matter, okay, knowledge as possible. Okay, so combine, and we can also have a way to combine similarity, the similarity measure, okay, depending on the nature of data that we have. At times we could have some set of data. We got categorical variable, we got ordinal, numerical, and so on. You got mixture of variables like that. And of course, you want to figure out, you want to find the similarity measure and approach that you can use is what I'm actually showcasing here that we call Goas distance. Okay, so one approach is to use an appropriate measure for each variable. Like you scale them to take the value in 0, 1, then you take a weighted average. And that's what you can see here. If this is the dissimilarity between SK and YK, so it's actually going to have a weight. And of course, we are dividing by that total weight. Okay, so allowing the weight WK to depend on the data now can actually undo missing data, okay, by setting that to 0. Okay, so back to the MDS right now. Of course, what are the requirements we need in the MDS? Okay, so I say here the only requirement is applying MDS is that some basis exist for rating or ranking the object in terms of their dissimilarity. Okay, now I told you the other time the object can be either observations or variables. Okay, so it depends on your intention. Okay, and I said if the goal is dimension reduction rather than visualization, because at times your goal may be to reduce the dimensionality, at times your goal is actually for you to have what I call very easy visualization. Okay, then we need to choose the embedding dimension D. and if possible, interpreting the meaning of dimension. Okay, so of course, you're actually gonna have the data set in multi-dimensional way. Okay, and of course, so you need a reduced dimension. Okay, maybe I'm gonna call that D. Now I'm going to walk us through an example now. Okay, so I'm going to take example of distance between European cities. Okay, you want to talk about, we got Athens in Greece, Berlin in Germany, Dublin in Ireland, London in United Kingdom, Madrid in Spain, Paris in France, Rome in Italy, and Warsaw in Poland. Now, when you look at the distance between them, this is what we have. Okay, of course, you're not surprised with 0, 0 in the diagonal because the distance between items and items is going to be 0. So when you take a look at this now, if I want to work with MDS, of course, my input data is going to be a distance matrix. Now, this is a distance matrix now. You know, we got a lot of dimension here. 1, 2, 3, 4, 5, 6, 7, 8. Is there a way we can actually, uh, you know, reduce the dimensionality here to 2 dimension, you know, for easy visualization, and in such a way, the distance between European city in the high dimensional space also going to be of, approximately the distance in the lower dimensional space. Now, I'm going to show you how to construct the map right now. So if you want to construct the map right now, this is you know the coding R. Okay, you can see my data set. It's actually city, and of course I actually want to use 2 dimension. Okay, don't forget the numbers of dimension I have: 1, 2, 3, 4, 5, 6, 7, 8. Okay, and I want to reduce that to 2. Now this is going to be the Q pip or Q plot that I'm actually going to generate. Now, when you take a look at this, plot right now, okay, you're going to see in the high dimensional data set, if you look at London and Paris, okay, London and Paris, they're very, very close, right? If you take a look at 213 in the higher dimensional space, but when you take a look at here, you're actually going to see that they are also close. Okay, so that is really makes sense. It's making sense. Now, when you take a look at Warsaw in Poland, okay, and Madrid in Spain, okay, the distance in the original, the dissimilarity in the original data set is 1,000. You can see that that's very huge, right? And of course, here in the lower dimensional space, you can actually see that is maintained as well. Okay, so and you know what? The MDS is going to give us the opportunity to see some city that are clustered together, and we're also going to have opportunity to see some city that are actually far away from each other. Okay, and of course, that is also going to be useful in gene sequencing, in gene expression, or where you're gonna, if you have different samples of genes that have different expression, you actually gonna see those ones that are clustered together. Okay, so what can we say about what we see right here? The original travel distance are not Euclidean, but we can approximate them with Euclidean distances on the reconstructed map. And of course, the meaning of the dimension here is quite clear. So which is, we're talking about the north-south and in east-west. Okay. And of course, how am I going to know that I've already have a successful reconstruction? I'm actually going to know if I have a successful reconstruction if the distance between the object in the higher dimensional space can approximately preserve in a lower dimensional space. Okay, and that was why I said the successful reconstruction is expected given that the original space is not that different from the Euclidean. Okay, so I'm going to go into another example right now, talk about visualizing similarity using MDS. Okay, we got this time around, we're going to work with gene expression data. Okay, we got 62 samples, okay, lymphoma samples, and each of these sample has 4,000 genes. Okay, and of course, we got 62 and 4,000 genes. That's a high dimensional data. Is there a way we can actually project this into two-dimensional space? Okay, and that was why I said we like to visualize similarity between the samples. And don't forget how many samples do we have? We got 62, and each of them has 4,000 genes. Now, I said a popular visualization technique in biology. To get this done is when you obtain correlation matrix. But the correlation matrix and you look at the corresponding heat map, you're going to be overwhelmed with the dimensionality issue in the data. And that was why I said, can we apply MDS to construct a 2D plot instead? But for you to be able to appreciate the significance of MDS, I needed to take a look at the heat map. This is the heat map from the same data. You can see I got 62 samples of genes, okay, lymphoma in particular, and you can see right here, this is not visible at all. Of course, you know, the correlation matrix, the heat map actually used intensity, color intensity, even though we'll be able to see the correlation between a particular pairs of genes, but one can be overwhelmed with this, and it's no, we need a very clear picture of how we can project, high dimensional data into lower dimensional space. And that's exactly what I'm doing here. Okay, so you know what I did? The other time I was talking about calculating the similarity from similarity. If the similarity is correlation, when I do one minus that, and of course, and I construct MDS based on that, this is what I'm going to have. You can see now I got two dimension. Take a look at that. And getting two dimension, we're able to project the samples of gene into the two dimension, which is a lower dimensional space. And that's going to give you opportunity to see some gene samples that are clustered together. Take a look at that. Okay, this is beautiful. Okay, so I'm actually gonna say this: we cannot eat our cake and have it, the distance in the higher dimensional space is not going to be the same distance in the lower dimensional space. Of course, how are we going to know whether we've done a great job in projecting, preserving the dissimilarity in the higher dimensional space into lower dimensional space? And because of that, we actually going to minimize, okay? If you take a look at, before we go into the optimization problem, if I want to go by classical MDS, okay, because we got different kind of MDS. Okay, we actually have a classical MDS, and of course, we also get another form of MDS, but the one that is very, very popular is a classical, MDS. Okay, now let me say in particular, we got a classical MDS. We also have a non-metric MDS. But you know what? In the classical MDS, we assume the dissimilarity data is metric, okay, and has exact distances, just like the one I showed you the other time, and we can find an optimal representation that minimizes stress. Okay, we're going to have a stress function. The stress function is actually going to more or less look like a sum of square error that we have in the conventional statistic. Okay, so if this is the dissimilarity initially, we actually are looking for n by p matches z. Okay, this very z right now is actually the coordinate in the lower dimensional space. Okay, so it's such that the dij square, the square of the dissimilarity in the high dimensional space, actually we can represent that this way. So take a look at that now. And of course, we know that that data now is calculated originally from X. I told you the input data is actually going to be a distance matrix. And of course, it can be any dissimilarity. Okay, so this is the MDS, and of course the classical MDS that we also call Togensen, Goa scaling. Okay, now the strategy here, don't forget, we actually want to minimize. Okay, our strategy is to derive some properties about Z satisfying this above equation and solve for it. And of course, the only relative distances matter, so we put the center of the column in Z at the origin. Of course, what we're going to do. I think the very first step is actually to figure out the coordinate in the lower dimensional space that I call Z. Okay, and of course, I'm actually going to walk you through how we can derive B, because when you have a B, decomposing B we actually give us the Z that we want, and we'll be able to perform the operation here. But how are we going to get B initially? This is how I'm actually going to walk you through the algebraic way to figure out B. Okay.